This is a fast little video for our first project in Pintos where we have to implement priority donation when it comes to locks. So priority donation is this idea that if you have a thread who has acquired a resource that a higher priority thread is waiting for, then that higher priority thread is effectively unable to progress except at the rate of the lower priority thread. So you have something of high priority, but it's being roadblocked by this thing of low priority that is waiting for the same resource, that has the resource it wants. So instead, it donates its priority to the lower priority thread so that it can progress to the point where it releases the resource. In Pintos's first project, the resource that we're concerned with are locks, which in Pintos are just binary semaphores with some extra semantics. They're essentially a binary semaphore where you can't call sema up unless you were the ones that previously called sema down. So it stores inside the lock the identity of who currently holds the lock. So let's have a lock here. I'll call it A, and it's a lock. And inside the lock object, there is a semaphore, because that's how they're implemented in Pintos. And with the semaphore, there is a list of waiters. It's some list. There's, of course, a semaphore value, but for the lock, it's just a binary value that starts with at 1, and there's a holder that starts out as null. Nobody holds it currently. And so we'll have threads. So let's say that there's a T1 thread, and it calls lock. And I'll say T1 has a priority, and we'll give it a low priority. We'll say 10. And there's T2. And T2 has its own priority, and we'll say that it has a higher priority, so like 63, the highest priority on Pintos. So T1 might acquire A, lock acquire, and because it's not a lock in contention, it would get it. So this arrow says that this resource is being held by T1. And so in Pintos, all that means is that it becomes the holder of the lock. And the value goes from 1 to 0, so that if T2 were to now request that lock, this is it wanting that lock, it's sema downing on a 0 semaphore, which means it blocks. And before it blocks, it adds itself to the list of waiters. So T2 is waiting for this lock. This is exactly the scenario where donation would occur. And what donation would do is say, okay, this higher priority thing, once it realizes it's waiting for something that T1 has, it would attempt to donate to T1. And what that means is it would do something that would cause T1's effective priority, right? And here I'm going to have to draw in like red, the effective priority is 63, whereas the effective priority of T2 is 63. Okay? And this is what the state would look like, where T2 is now blocked, it's yielded the CPU, but now T1 could progress and eventually reach the point in T1's program where it releases the lock, where it would take itself out as the holder, set this to null. It would take someone off the waiters list and say that they should go next, And now 63 would be able to run at some point, and it would be able to acquire the lock A. It would take itself out of the waiters list, it would set itself up as the holder, etc., etc., etc. But on this release, on this lock release, it must be the case that T1 drops the donated priority and goes back to its effective priority of 10. That's a very simple situation. I'll go through a more complex situation in the next one.